So now let's take a brief look at the review for the first midterm in Physics 8B. There are going to be 3 problems on the midterm, just like the sample test. Okay, and we'll cover chapters 15, 16, and 17. Now there are 2 parts in chapter 16, but it doesn't mean you necessarily get 2 problems in chapter 16. So we're going to review chapter 16 as a single chapter. Now, first of all, what should you consider important in chapter 15? Well, the chapter 15 is all about oscillations, and we're going to focus on simple harmonic oscillation. Right? For the simple harmonic oscillation, you should be familiar with the 2 most common examples: so-called standard simple harmonic motion system. One is the spring and mass system. The other is the simple pendulum. You should know how to establish the equations of motion for both of them, and how to solve these equations to yield your answers, including the expression for the frequency / period, right? Like, an angular frequency omega equal to square root of k over m, and square root of g over l for both cases. Also express x, v, and a, the displacement, velocity, and acceleration as functions of time. Okay, and that's from force and torque point of view. You should also make sure you understand how to solve the same problem from energy point of view, from kinetic and potential energy. Now, the kinetic energy is always 1/2 mv squared, or 1/2 I omega squared if it's rotation. But the potential energy can assume all types of forms. But for a simple harmonic system, the potential energy must be of the order of 1/2 kx squared. This k doesn't have to be exactly the spring constant; it could be something equivalent, just a positive number. And this x doesn't have to be x; it could be theta, it could be any other sort of displacement. But the potential energy must go like a positive, must go like a parabolic function with a positive coefficient. It must go like something positive constant times displacement squared. Okay, if the potential is like that, you're going to get yourself a simple harmonic system. So that's from the 2 standard systems, and you can go beyond the 2 standard systems. You can look at cases where, as the examples that we gave, you can have a spring attached to a rod. The rod also can oscillate because of gravity. So you actually have to combine the force of the spring and the force of gravity. Right? You can think of any number of systems that will eventually do simple harmonic oscillation, and you should know how to prove that something is undergoing simple harmonic oscillation. And there are 2 general methods for doing that. One is use the force / torque method. The other is to use the energy method. Now, when do you use force? When do you use torque? Well, you use torque method if there is an unknown force that you cannot find out. For example, a physical pendulum, right? There's a force at the pivot. You clearly don't know what that force is, but it's an external force that has to be considered if you use F equals ma. So we are going to have to use the torque method because there is no torque of that force at the pivot. We use the pivot as a reference point to calculate the torque, right? The other method is energy method. You just basically write down the energy of the system, which includes the kinetic energy and the potential energy. Now, there could be more than 1 term in the potential energy. You could have, for example, gravitational potential energy and elastic potential energy and whatever. Okay, but at the end of the day, when you write down the energy expression, it has to be the kinetic energy term, which is a quadratic term for v squared, plus another quadratic term for potential energy, which should be positive constant times displacement squared. Okay, and if you get that, it's got to be a simple harmonic oscillation. And as far as the frequency is concerned, or the period is concerned, once you write down the standard equation of motion or the standard energy expression, once you write down the energy expression or the force or torque equation for the system, you don't have to proceed by solving it from scratch. All you have to do is compare with the standard expression for either force / torque or energy from the 2 systems that we studied before, the mass spring system and the single pendulum system. All you have to do is get the equivalent mass and the equivalent spring constant, and you get your result. Okay, by comparing with the standard system. All right, now as far as the calculations are concerned, this is pretty much what you need to be thinking of for chapter 15. As far as damp and forced oscillations, we don't require any numerical analysis for the midterm. You have to understand the basic qualitative ideas. When you have a damping, it's going to have two effects on the system. One is it's going to reduce the amplitude over time, and secondly, it's going to decrease the average speed. Therefore, it will prolong the period or decrease the frequency. Okay. Another thing of importance when it comes to forced oscillation, if you're driving the system with a simple harmonic force of its own frequency, then a resonance would take place if the system, if the driving force has the same frequency as the natural frequency of the system. That's called resonance. All right, but that's only qualitative analysis. Now, chapter 16, both parts 1 and 2. We start with the generic wave equation. You know, we saw different flavors of that. They all lead to the same general equation. The wave on a string, the wave in a horizontal in a long spring, and also the sound wave in an air column. Right. The derivations are different, and they're very important to our understanding of the wave phenomenon. But I'm not going to put a derivation of the wave equation in the test. What you need to do, though, is to understand the features or characteristics of the solution, as well as the expression for the wave speed. The features of the solution. The solution of the wave equation is the most general solution of any common differential equations. Okay, it's just, you know, it's any differential function f with an argument of x plus or minus vt. Okay, and v here is the speed of the wave, and the speed of elastic wave is always the square root of some sort of elastic modulus divided by some sort of inertial parameter, which, in other words, density. That's something you should know in general. Okay. Now, if you focus on a simple harmonic solution of the wave equation, we get yourself a simple harmonic wave. For simple harmonic wave, we have these important parameters such as the wavelength, the period, frequency, and the wave speed. Now, make sure you know how to find the connection between these quantities. For example, lambda equals v times t or v over f, and so on. Okay, and the general solution to the simple harmonic wave is like x equals amplitude times sine or cosine times the phase angle, and there are different expressions for the phase angle, such as kx minus omega t. You should be familiar with these different expressions. Okay, intensity of the wave. There are detailed derivations about the intensity carried by your simple harmonic wave. We're not going to go through the detailed derivation during the test, but you need to know that intensity is defined as power emitted by the wave per unit cross-section area, and it is proportional to the amplitude squared of the wave. That's something you definitely have to know. Okay, intensity is proportional to amplitude squared. And when it comes to sound wave, there is something special called sound level, and that is the perceived loudness of the sound as a function of the intensity. You should know that. You know, the expression for the log function. Okay, and the Doppler effect is not unique to sound, but it's something very important when it comes to sound waves. It is the shift in perceived frequency away from the frequency emitted by the source. And that could be due to the motion of the source, the motion of the observer, or both. Okay, you should know the general formula when both the observer and the source are moving, and there are plus or minus signs to be determined in the general expression. And the trick to determining these signs is to do them one at a time, right? If you want to determine, you know, how the motion of the source affects the Doppler shift, you can ignore the motion of the observer, only consider the motion of the source, and you can see whether you use a plus or minus sign, because you will know what happens when the source moves. Does it increase or decrease the frequency? I mean, if the source moves towards the observer, that'll increase the frequency heard by the observer. So that will help you determine what sign to use. Okay. And There's also the effect of the wind. The Doppler effect formula we derived is in the presence of no wind, which means the air or the medium is at rest. And what happens when the medium moves? Simple, just follow the wind, follow the medium movement, so that in this new reference frame, both the velocity of the source and reservoir will change because of relative motion, but the formula could be used one more time. Okay, so be careful about that. And as far as chapter 17 is concerned, which is basically, add more than one waves up, especially in the case of two waves. When you add waves up, you have to follow the superposition principle. But in most cases, when you add two waves up, you don't get a stable pattern of alternating strong and weak signals. That is called an interference pattern. The interference pattern is a stable pattern that can only happen when the two waves being added are considered coherent. Okay, and we can see many applications of that. And the two most common used examples are wave on a string or wave in an air column, which we use for musical instruments. Okay, so we get yourself a standing wave when the two waves being added travel in opposite directions. All right, and then we have these nodes and antinodes, and between nodes we have what's called a loop, and each loop is half wavelengths long. You have to know that, and you also have to know the boundary conditions for either the air column or the string or a string. There are two cases where, if the end is fixed or if the end is open, you have different conditions. Okay, you have different conditions for these boundary conditions. And either way, from the boundary conditions, you can determine the so-called resonance frequencies, and that is at what frequencies will the air column or the string give you a strong oscillation. You should be able to draw these patterns like one loop, two loop, if both ends are fixed, or in the case of an air column with one loop, one side open, the other side closed, then you will have a node at one end, an antinode at the other end, just like the lab that we did. Okay, and when it comes to sound waves, it's more complicated than a wave on a string, because there are two parameters we can use to describe the sound waves, either a displacement or a pressure. Okay, and pressure and displacement do not reach maximum at the same point. When the pressure variation is zero, the displacement is actually a maximum. And when the displacement is a maximum, it means the air molecules cannot move, they're trapped. And that's where the pressure due to the sound actually reaches an antinode or maximum. All right, another important special case is beats. And that's when you add two waves of slightly different frequency at the same location. So you will get a variation of intensity over time. So it is an interference over time, not over space. Okay, so you do not see or hear, you do not see variation of intensity from location to location. Rather, you hear variation of intensity from one moment to another moment, and you have what's called a beat frequency, which is the difference between the two slightly different frequencies. Okay, so that's something we also have to pay attention to. So again, 3 problems, they're of equal number of points. And if you understand these topics that we just reviewed, you should be fine for the midterm. Okay. Oh, it's 90 minutes, 1.5 hours. That's average of half an hour for each problem. There's plenty of time. Closed book, closed notes, but I will provide you with a formula sheet, and you can use a scientific calculator. Or any fancy ones are permitted as long as they don't have internet connection. Okay, so that's the review.